Okay, we're going to go through this January's exam, Edexcel Physics, Unit 4, Further Mechanics, Fields and Particles. So these students in Year 13 probably took this exam if you're in Year 13 doing the International A level. You probably took this exam in January, and this is probably the first look you'll get at how you did. You've probably seen your grades by now, and you are deciding whether you want to reset it. Okay, as you know, it starts with 10 multiple choice questions. So the first one is a nice warm-up. It says which of the following is the number of neutrons in a nucleus of SB121. Well, to work out the number of neutrons, it's A minus Z. A is the big number, Z is the small number. Z means the number of protons in a nucleus, and A is the total number of nucleons. So take away one from the other, you'll get B. Okay. The next question is also a knowledge question. Which is the process by which electrons are released from a heated filament? These are used in cathode ray tubes. Cathode ray means a negative ray. So if you want to produce a beam of electrons, the process is called thermionic emission. Therm means heat. So you create an ion and you emit an electron. Okay, so this is just knowledge. You can go through the rest of the answers if you wish, but you just need to know these. These are just quick answers, so it saves you time to put towards the more difficult questions. The next question is question 3, and I just need to move it down a bit so you can see it's not on the camera as I've zoomed in. So this time it's about a proton traveling at speed v. This is it, a positive proton moving at speed v, enters a uniform magnetic field. Uniform means that the field lines are parallel to each other, and it means the field strength is also constant if it's shown as parallel lines. The magnetic flux density of the field is given as 45 milliteslas, as shown. So here's the 45 milliteslas, so that's 10 to the minus 3 teslas. And then it says a force of this much, 1.35 times 10 to the minus 3 newtons is exerted on the proton as it travels through the magnetic field, obviously. Which of the following expressions gives V in meters per second? So this is about the force on a moving charge, magnetic field strength, the charge, and the velocity, this BQV. So if you want to know the velocity, it's the force divided by B times Q. Okay, so that's basically what you could do. Put the numbers in. The force is given to you here, divided by the magnetic field strength, 45 times 10 to the minus 3. And the charge on a proton is the same as the charge on an electron. It's 1.6 times 10 to the minus 19 coulombs. So once you do that, you'll see the answer is C. So again, they want you to check that you know the BQV equation. These equations are given to you on the equation sheet. Question 4. It's about nucleons. The structure of nucleons, it says, can be investigated using high energy electrons. Okay. So high energy means high velocity, obviously, because it's high energy means high kinetic energy, high velocity, and high velocity means high momentum. So this is going to talk about de Broglie's wavelength. Which of the following is the reason high energies are needed? If you don't have high energies, you won't have high momentum. If you don't have a high momentum, you will not have a small enough wavelength to penetrate the nucleons. Remember, nucleons are of the order of 10 to the minus 15 meters. So the answer is to produce a short de Broglie wavelength. It's pronounced de Broglie, I believe, French name. So all the others are incorrect. Okay, so if you probably can't get access to the mark scheme, but obviously the rest are just ridiculous. It's about de Broglie. To cause annihilation, no, it's nothing to do with annihilation. They're just seeing who's revised and who hasn't. To produce individual quarks, no, they don't produce individual quarks. You can't have individual quarks. They always come in combinations. Or it says to overcome repulsive electrostatic forces. It's just an irrelevant answer. The only answer that makes sense is to produce short de Broglie wavelength. If the wavelength is small enough, it means it can penetrate more deeply. Okay, that's how electron microscopes work. They have a shorter wavelength than visible light, so therefore they're more penetrating and can see smaller objects, or see being possibly the wrong term to use because you don't actually see other than with your eyes. Okay, so a potential difference is applied across two parallel metal plates. Parallel metal plates have a uniform field in them. Okay, parallel plates, the electric field strength is the voltage divided the distance between them. Which of the following graphs shows how the electric field varies with distance d from the positive plate? So if one is the positive plate, doesn't matter which one. I've drawn the field line, so it would be a direction a positive charge would move. Therefore, this is a negative, so I've drawn the arrows in the right direction compared to the charges. So if you have this uniform field in there, that means the electric field strength doesn't vary between them. So therefore, the electric field strength is constant. So it has to be A. Yeah, constant E. None of the rest are constant. Now, next question is about a pion. A pion can decay into two leptons. Okay, so you need to know what a lepton is. One thing, so they've actually, all the answers give leptons. Okay, electrons, positrons, neutrinos and antineutrinos are shown. All of these are leptons. Lepton means light particles, as opposed to heavy particles, which are made of quarks. So he wants you to work out which of the following decays is possible. So you need to check the conservation rules are satisfied. So the first thing I did was to see if charge is conserved. We have a negative charge here, a negative charge there. This is neutral, so charge is conserved. And then these ones aren't. You've got a neutral pion, becomes a negative electron, so the charge is not conserved, so no, it's not B. C, likewise, charge is not conserved. It says it's a neutral pion, and it turns into a positron, which is not possible because you can't create a charge from nowhere. So it's either going to be A or D. D, the lepton numbers don't add up because to create a lepton, if the two leptons one must be a lepton and one must be an anti-lepton to conserve the numbers. You can't have two leptons produced. Well, this is a lepton because it's an electron, and this is also a lepton because it's got no bar on it. So lepton number is not conserved. That means A is wrong. D must be correct. And you can see here you've got an anti-lepton. Yeah, it's a positron, which is an anti-electron. So anti-particles give lepton numbers of -1. And this is an electron neutrino, which hasn't got a bar on it. So it is a lepton. So it's +1. +1 and -1, they cancel out. So you have a neutral number of leptons, total number 0 lepton numbers. So this is the only one that conserves both rules. So you don't need to go any further, and D is the right answer. Question 7 is about two capacitors in series, and they just want you to know what is the equation for capacitors in series. So it says a potential difference connected across a single capacitor, capacitance C. The charge stored on it is Q because the equation is QCV. Q equals CV. The capacitor is then replaced with two capacitors, each of capacitance same C, connected in parallel. So they want to know if you understand the capacitors in parallel. So capacitance doubles in parallel. C total is C1 plus C2. Yeah. If the capacitance doubles, it means your ability to store charge doubles. So you can store being a loosely used term because you're actually not storing it. You're separating the charge between the positive side of the battery and the negative side. So it actually separates charges out. So you're kind of storing electrical energy in the capacitor temporarily. So each one gets a charge of Q. So the total charge is 2Q. Okay, D. By the way, I recommend listening to these videos at 1.5 speed because when I'm talking, obviously I'm talking at normal speed, but when you're listening, you can get through it at 1.5 times as fast by going through it, putting the speed at 1.5. I think it actually sounds better at a higher speed. Okay, I always listen to the videos at 1.5 speeds. If you get stuck and you want to go through something, of course you can pause the video. Now this is about a magnet moving away from a coil as shown. So direction of movement is this way, yeah, as shown by this arrow, and they want you to work out what's happening. A current is produced in the coil XY, which creates a magnetic field around the coil. Okay, so if you have a magnetic field that's moving, then it's going to induce an EMF and therefore a current in the coil. So whenever you have that, the direction of the magnetic field can be worked out. Okay, but it's actually quite an easy question if you know the rules. Which row of the table shows the magnetic pole at X and the magnetic pole at Y? They want you to make sure you got it the right way around. Well, obviously they have to be the opposites, so it can't be north-north and it can't be south-south, so it has to be B and C. So this is all about Lenz's law. Okay, the magnet is pulling itself away from the coil. So Lenz's law says it will oppose the change that's causing it. Okay, well, the change that's causing it is the magnet moving out. So the pole here will act to try to pull back the south pole to resist the change that's causing the field in there. So the answer will be an attraction at X, so it must be north, and of course there must be different poles at each side, and it will be south. So the answer is B. The magnetic field created will oppose the magnet being pulled away. Okay, if you're pushing it in, it would become a south pole, but if you're pulling it out, it becomes north pole. It will do the opposite to what you're trying to do. It will try to oppose you. Okay, that's the conservation of law implication. Question 9 is about change in momentum. It says a helium atom of mass m and velocity v collides at right angles, so you don't have to do any resolution, with the surface as shown. Here's a surface, it goes there, and then it bounces off the surface with the same speed but in the opposite direction. So the only thing is, how do you decide on what is the positive direction and the negative direction in this question? So once you do the maths, you'll be able to work out that the magnitude is easy. It's just a matter of then deciding which one it is. So which of the following is the mean force applied to the atom during the collision? So during the collision is actually in the surface. So force is change in momentum divided by the time taken. The time taken is delta t. So I've put the change in momentum is negative. To start with, final momentum is negative. So I put after is negative and before must have been positive. That's a way of doing it. And delta t, so it's minus mv again. So it's minus 2mv divided by t, which should give you the answer D. Now, a change of momentum quantitatively, of course, it could be B as well. So I've put negative force is in opposite direction to the original velocity. So you want to show that you know the force is the cause of the change in momentum. Okay, so I think most people will get D if they've done the maths correctly. Finally, question D is about an alpha particle bouncing off a gold nucleus. Gold nucleus is 79 protons and alpha particle is 2 protons. So if it goes, A goes there, yeah? A is going the wrong direction, so you know it can't be A. They want you to work out what's going to happen. The B is the direction of the solid line that shows what happens when an alpha particle goes this close to the gold nucleus. So there's your closest separation between the gold and the alpha. So it deflects it away. So the alpha particle there. Let's say now a second alpha particle with the same kinetic energy, so same initial velocity, approaches the gold nucleus. Which dotted line shows a possible path for the second alpha particle? Okay, well, A is the wrong direction because it's attracting, and obviously we know they're both positive. So A is wrong, and D is wrong because D is going in the wrong direction as well. So D, if it was coming from this side, D would go this way. It's not going to bounce and go left. It's going to go that way, D. So D is wrong, A is wrong. And B is going closer to the gold nucleus, but the deflection is weaker than the solid line. So the deflection is too small. So only C, which also goes closer to the gold nucleus, you can see the closest position is there. The force must be greater, so the deflection must be greater, so therefore only C is correct. Okay, that's the 10 multiple choice questions done. Okay, we'll do a few more in the first video. I'll then upload that to YouTube, and then we'll do the rest of it, the questions, in a second and possibly a third video, because as we go through the section B, the question get longer and get more complicated. And part of doing these videos is to help you understand the theory that you may have misconceptions about. Okay, so this is about capacitors. The first question, it's only 3 marks, so it goes from 1 mark multiple choice questions to shorter questions, and then they get longer questions with multiple parts in them as you get towards the end. You probably noticed if you revised with previous papers. So a student selects the capacitor shown to use in a circuit. So you can see it's got 2,200 microfarads written on it and 25 volts. So that's this operating voltage, and it mentions there's 2,200 microfarads, which 10 to the minus 6. It then says a tolerance of the capacitor is plus or minus 20%. So that means it will either be 2,200 microfarads plus 20% maximum, or 2,200 minus 20% of 2,200 minimum. So they want you to calculate the maximum energy such a capacitor can store. So we're given the values which I've just shown you on the screen, but to get the maximum capacitance would be the case where the tolerance is gone to the maximum possible by the manufacturer, claiming that the value given on here, it could be out by 20% each way. So the maximum possible capacitance would be 1.2 times 2,200 microfarads. So you're basically multiplied by 1.2, which is a 20% increase, or 120%. Once you do that, you get a mark for knowing that you've got to do that. So that comes out to capacitance of 2,640. Then if you want to work out the energy, obviously you've got to use the maximum value that you just worked out, and that will give you the maximum energy stored using half CV squared, because we know C, we know V, and this is on your equation sheet. So half times the value, 2,640 microfarads, times 25 squared. Okay, one of my students who took this exam, unfortunately, just simply forgot to square it, I think. So that could lose you marks. So if you do it on a calculator, it'll come to about 0.825, and you should really round that up to 0.83, because the tolerance is only 20% anyway, so you don't know the things accurately. And you can see they've only given 2 significant figures here and 2 significant figures there, so you shouldn't really give 3 significant figures. So there's your 3 marks. Okay. Question 12. This was another point of confusion for people who took this exam. I haven't looked at the examiner's report yet. These are also available on the Pearson website. The diagram shows tracks produced by particles in a bubble chamber. Okay. Now bubble chambers work when charged particles move through them. They leave a track because it kind of attracts the positivity attracts these bubbles to form around them, a bit like a jet trail an aircraft produces when it has the condensation trails produced behind the exhaust fumes at high altitude where the temperature is lower. So it's kind of a condensation. Now you'll notice it says a charged particle interacts with a stationary proton at P. So P is where the stationary proton is. This produces 2 neutral particles. Okay? So 2 neutral particles. Each of these neutral particles is unstable and eventually decays into other particles. See my dotted lines that I've written there. So basically, the neutral particles must be going this way. Now the initial particle comes in at this way, so obviously it makes sense that they're going to continue to move off after the deflection of the proton. So that shows the charged particle before colliding at P and then it produced 2 neutral particles. That's the first thing you've got to realize. It says explain the evidence provided by diagram for this description of the interactions. Only charged particles leave tracks, so the neutral particles don't, and that's why you don't see anything from the point of collision at P until the neutral particles decay. So my dotted lines show, I put that, you don't have to say that, but I think putting dotted lines on there to show them that you know what you're doing, show the paths neutral particles must have taken, before they decay, okay? And the decays are shown as V-shaped points on the diagram, okay? So here's a V-shaped point, and here's a V-shaped point. So there you have each of these particles. There's 2 of them, yeah? 2 neutral ones. There's 1, there's 2 decaying. So they decay as the V-shaped particles. You'll get a mark for that. You'll get a mark for understanding that neutral particles don't leave tracks. So I've replaced that with dotted lines just to show them that I know that. And then it says particle must have decayed into 2 charged particles and continued movement up the diagram, and I put an extra clarification. That's a conservation of momentum. Yeah, obviously if the particle came in from the bottom, hit a stationary particle, it would then continue roughly in the same direction. So I hope that makes sense to you. Just to show you the diagram again. Okay, so that's what you've got to be able to explain for the 3 marks. Question 13. In the early universe, it says, just bring it down a bit, a helium molecule, that presumably means 2 helium atom, formed when a proton joined with a helium atom, okay? It says the helium atom in the helium molecule could lose both of its electrons in a collision. Okay, when this happens, the helium ion and the proton accelerate away from each other. So it doesn't really stay as a molecule. They collide, they interact, and then they repel because they're both positive. So we know what's going on. The initial separation of the helium ion and the proton was 7.9 × 10⁻11, which is R. Okay. Calculate the initial force between them. Well, that's Coulomb's law. F equals K, which is constant of proportionality. Q1, charge 1. I put that as the helium. Charge 2, proton. So I put these big Q 1 and big Q2 because that's how it's recorded in the list of equations that you have on the back of the paper. Now, this K happens to be 1/4πε0. That's where it comes from. But obviously it's quicker than dividing by 4π and epsilon0. You can just use a data sheet to give you what 1/4πε0 is. So it's a shortcut in your calculation. You need to save time whenever you can. Now, remember, the charges is a double charge for helium and a single charge for protons. So there's 2 times the charge of an electron or a proton, and this is single. So you've got to make sure you've got that in, divided by the distance they've given you, which is in meters already. Put the numbers in, you'll get a mark. Put the answer, 7.38. Yeah, again, it should be to 2 significant figures because the data they've given you is 2 significant figures. And this is 2 significant figures. So 2 is the common one. If you put 3, they probably will give you the mark. But that's how you decide how many significant figures to use. Part B, calculate the electric field strength due to the helium ion at the initial position of the proton. Well, the electric field strength is basically the force you've calculated divided by the charge of hydrogen, the second charge, which is a unit positive charge anyway. So electric field is force per coulomb, newtons per coulomb, so the answer will be in newtons per coulomb. So you just divide what you just calculated. I'll use the 3 significant figure answer, divided by the charge of hydrogen, and you'll get the field strength at that position. Okay? Obviously, the field strength is radially controlled, so it's basically getting weaker as you go further away. That's why it's saying at the initial position of the proton, which is where we calculated the force. Okay? I hope that makes sense. So again, this is another short question, it's 4 marks. And now it's on to the Rutherford scattering question, which is a very, very common question in paper 4. So we're going to just read through it first. In the early 20th century, Rutherford carried out a series of experiments in which alpha particles were directed at a thin gold foil. They just put thin metal foil. A simplified version of the apparatus is shown. So here's the alpha particles firing there, and here you've got a detector, so the alpha particles go there. Most of them go straight through. A few of them get deflected, and you can move the detector to statistically work out how many go straight through and how many get deflected. Okay, and very rarely, 1 in about 8,000, hit directly a gold nucleus. We now know what it is. It hits the gold nucleus and rebounds due to the theory we just went through in the previous question. Okay, so they want you to describe the observations and the conclusions that resulted from the observations, okay, that they came up with. So I put the observations on this side and I put the conclusions on that side. So most alpha particles went straight through, 1 mark. That's an observation. So atom must be mostly empty space. First conclusion. A few alpha particles, this means ditto. I was surprised one of my year 11 students didn't know when he was going through one of my YouTube videos. He didn't know what this sign meant. This means the same as the word above. A few alpha particles were deflected by small angles. Another observation. Very few were deflected by angles greater than 90, i.e. very few rebounded. I told you that was about what I always teach my students is 1 in 8,000, statistically speaking. So this is the final conclusion. And so we've had 3 observations, 1 conclusion. So there must be a concentration of mass in the atom. Yeah. So you could say it's just the mass hitting another mass which causes the large deflections or the rebounding. But to me, it must be clear that it must be positive charge. I believe they knew the alpha particles were positive charge from the direction alpha particles deflected in a magnetic field. So I think they already knew that at the time. It's about 1912, 1911, something like that. So it must be positively charged, I've put, but as long as you say it must be charged to cause the particles to rebound. Okay. Anyway, that's basically what they're looking for. I put a little note here to show you the mark scheme for this question. So let me just quickly find that to see. I may have simplified some of the answers that they'll accept. Okay. So question 14 on the mark scheme, if you want to stop the video and have a look at it, that's how they mark it. So it's basically what I said. So the final mark is the most tricky one to explain it, but looks like they're being quite lenient. So usually my students know this question is coming up and they tend to do well on this question. Okay, that's just stop the video if you want to look at exactly what the mark scheme was saying. Okay, question 15 is also a short question, so we'll stop when we get to the long questions because it's 22 questions in total. And this is really only for students who've taken this exam before. It's better not to use the most recent ones if you're preparing for the module, say, for the first time, because your teachers may want to use it as a practice exam. Okay, so here you have a beam of electrons directed towards a graphite, a thin piece of graphite, and then towards a fluorescent screen, as shown in the apparatus. So here is where you have thermionic emission occurring. There you've got a heater, so you heat this usually with a small voltage, so it has its own, normally about 6 volts here, just for the filament. So you're heating it, and then you accelerate it. Some electrons escape due to the thermionic emission, which we saw in multiple choice question 2. The electrons kind of get to the surface and then they get attracted to a high voltage anode here. So this is negative, this is positive, and then they kind of go through the gap, hit that, and then they kind of create what's the word? Interference pattern. Okay, so a diffraction pattern was produced on the fluorescent screen. Yeah, so you'll have a central bright area, and around it you'll have concentric circles, as the particles diffract through the graphite. Okay, so remember, this is now showing that electrons behave a bit like, have wave-like properties. So we know that from the diffraction pattern, the de Broglie wavelength of the electron beam was determined to be lambda, which is 2.55 times 10 to the minus 11. So we know that de Broglie is lambda equals h over p. That's the de Broglie, so you can work out the momentum. So the first thing you could do is just put automatically work out what the momentum of the particles must be. So you'll get at least 1 mark for doing that part of it. I haven't looked at the mark scheme carefully to see where they come from. It then wants you to calculate the voltage. So we know that the electrons which are causing the diffraction or have the momentum of this much. Once you also can use, so we know that the voltage is linked to the energy of the electrons by the equation energy equals charge times voltage. Okay, so that basically is how you accelerate them. With this voltage, they'll accelerate and they'll go through. So we want to work out what was the voltage that produced the momentum that we're talking about. So we know that if the particles have gained energy, the energy they gained by the voltage becomes kinetic energy. Okay, so work done electrically produces kinetic energy particles, and you can have the equation, which is a shortcut again. The kinetic energy of the particles is the p momentum squared divided by 2m. You can also just do it the long way round if you're confused about this equation, but you should really need to revise this so you know. It's basically combining half mv squared and then replacing the v with momentum. Okay, so it allows you to do the answer more quickly. We worked out p before, so you now square it and then divide it by 2m to work out the kinetic energy. You then say the kinetic energy is in joules, so we know this is this side of it. We know the charge is for an electron is 1.6 times 10 to the minus 19. So you change the equation round. So V would be kinetic energy divided by charge. So there's the kinetic energy. There's the charge of an electron. And that comes out 2,319. I've deliberately put it as 4 significant figures. And then to show you, you can either use 3 or 2 significant figures in your final answer. Okay, that gives you the 4 marks, and they'll probably be divided somehow between the different stages of this question. Say 1 for that, 1 for knowing this, and 1 for getting the final answer would be how I would do it. Okay. All right, so we have another short question. This time it's another 4 marker. So it's question 16, and it says an aeroplane flies through the Earth's magnetic field. An EMF is induced across his wingtips. Wingtips are 35 meters across. The aeroplane is flying with a velocity v at 90 degrees to the vertical component of the Earth's magnetic field. So they're by telling us 90 degrees, so we don't have to do any sine theta in the equation. The distance between tips is given, so that's L. An EMF of 0.4 volts, 0.40 volts is induced across the tips. Okay, the pilot states that the aeroplane is flying with a speed of 250 meters per second. Okay, deduce whether the magnitude of the EMF supports the pilot's statement. In other words, if the EMF is 0.40 volts, what speed should that indicate? Because remember, the rate of cutting the field is the EMF induced. So the EMF induced is the rate at which the plane is cutting through the field lines. And because they're right angles, you don't need to have any sine theta in there. So it's BA over delta T. There is no N in this equation because it's just, there's no turns involved in the wings of the plane. So we're using the length across the plane as the length, length of the conductor. Now, area over time would be the length multiplied by the velocity, because obviously velocity times length will sweep out an area per second. So this is what they want you to show that you know, because I've taught my students this is another shortcut, and this is equivalent to BA over delta T, because V is meters per second, so that brings in the delta T in there, and LV is the A over delta T. So you need to show that you understand that. So I think they penalized one of my students for going straight in there, because you could go straight in there. They want you to show that you know it's linked with the rate of flux linkage. Okay, put the answers in, you'll get it to be 279 meters per second, which is greater than 250. So the pilot's statement is incorrect. So you'll probably get 1 mark for showing that you know that, and 1 mark for putting the numbers in, 1 for the answer, 1 for conclusion. Okay, so that's how you get your 4 marks in question 16. Okay, question 17 is a multi-part question, and it's about circular motion. So we will stop there, and we will upload this video for you. So please, if you found it useful, please share it with your friends if you have friends who are doing the same exam, so that they can get use of this as well. But remember, you should only do this exam if you just want to know what you did wrong when you took it the first time round. Don't use it for preparing for mocks right now, because your teachers may want you to see how you would do if you're using this for the first time. Okay, so please like and share, and then subscribe, and it will let you be notified on when the second video will be ready. Okay, thank you very much for watching, and hopefully see you in the next video. Remember, listen at 1.5 speed, it will be much quicker. Bye.